Thank you everyone for coming. It's really good to talk after Arash as well because he gives a massive overview about the field, so it makes my job a little bit easier. So I'm talking a little bit about what Arash was talking in the end, so the physical interaction. And the physical interaction between humans and robots, and how to make it, how we make it to get that connection closer, and my perspective of it. And it's because of my perspective, I'm going to talk just a little bit before my childhood. This is the robots I grew up with. This is my first robot as a PhD student. Not the greatest robot who plays with the Baxter, but it's amazing to play, easy to break and fix. And this is years later with master students working at Deadline for Arrows. And this was, they were recording to show for their family. So they were finally working. This is 4 a.m. in the deadline. I am dead, asleep, laughing because they're making jokes about the theory. And at 4 a.m. they were showing, really recording, the 2 students recording to show to the family. And it's Bavaria, so it was beer, actual beer. And yeah, it's just to show that when you come to physical human-robot interaction, it's not that easy. Human-robot interaction, then you add the human part, you make it a little bit more difficult. So where it comes from? It comes that it's a completely new field, yes. When you compare with robotics, and these are the graphs for robotics, and you can see the numbers in the top, like you're talking about 30K papers per year nowadays. And I'm sure that this is 2 years ago, so it's way more than that. And when you come to human-robot interaction, we are talking about just starting on the 2000s and physical human-robot interaction 15 years ago. So we're still in the early ages of the topic, of the field, and getting everybody to join because it's a very exciting one. So how we make this connection, how we make robots more reliable so that those scenarios doesn't happen. Don't draw beers in your supervisor, that's a start. ChatGPT for sure will be there in all the fields. But my perspective is more layered approach, and here I'm talking about those topics. So I see human-robot interaction through a layered scenario, what you need to have in terms of safety, in terms of understanding and reactions, so understanding tasks. And this is the topic that I'll talk about less because it's less connected to the topic, but I'll talk more about the safety layers and the team player layer. So how we connect to people. And this needs to be one on top of the other. So the basic features, the safety layer. And when you talk about safety, the first thing that comes, of course, you have cognitive safety, you have many aspects of safety, but the most critical one is physical safety. So what happens if you have a collision, and this is well known, so decades of years of collision studies, hundreds of years of collision studies, we know that there is 2 spaces that we can control. We can control the pre-collision phase, which basically imagine yourself driving a car, what you do, you brake. And this is one of the scenarios we could do. With manipulators, I will show that we can do a little bit more than that. During the collision phase, it's just transmission of energy. Is where your car crashed. There is nothing you can do there. But there is what you can do after the collision. So I'll talk a little bit about those 2. And the pre-collision phase, what I was mentioning, the velocity shaping is the most standard approach. You just reduce the velocity, you reduce the energy. That's very trivial. And of course, it depends on the material you have, the curvature, if you have a knife, or if you have a rubber around you, that's completely different. But the other thing that you could do is adapting the reflected mass. So think about yourself as a boxer. As a boxer, you try to maximize damage. So you have a behavior, a posture that maximizes your reflected mass. As a robot, you wanted to have the opposite of that. You wanted to have scenarios where you have lower reflected mass, because if you have lower reflected mass, you can have higher velocities. And this curve in the top right is just a reflection of that. So if you consider what is called safety curves, not going too much detail about that, but it's basically the relationship about the velocity you can have that is still safe according to the reflected mass that you have. And here you can see if you have a lower reflected mass, you can go faster. And this is just a very trivial time optimal controller. In the blue line, you see the direction that it goes if it's a straight line from start to go. And the blue line is the time it takes, the safety time it takes. Because the straight line has higher reflected mass, the robot, to be safe, needs to go slower. But if you take the longer path, the path in red, that results in a much lower reflected mass, which allows you to go much faster. So you can actually do the job much quicker. So we embedded that into different planners. This is just an example of an A-star, a modified A-star, that instead of having the heuristics on the distance, we have heuristics on the time, the transition time, the safety transition time. And these are the results we got. So you see that if you just do velocity shaping in the top figure, that's really bad. It takes a lot of time, because basically the time, the direction that you take, it's one that is high reflected mass. That requires you to reduce your speed quite a lot. The second one is breaking the safety, and that's not acceptable. And the third one is using the S-star planner that I mentioned just now. So this is the different trajectory. So it's basically modifying the time optimal trajectory to be in a safe trajectory. Now, I'm going to talk a little bit more now on the other side of the challenge in the post-collision phase. In the post-collision phase, we'll talk about reflexes that the robot can take. So this is an example. There is a collision, the robot just contact the person and adds this super zero-G behavior that removes all the mass, the reflected mass from the robot. So here, what we did first was to design a taxonomy. So we look on previous studies, we design what different scenarios between human-robot interaction could cause safety issues. Build up a massive taxonomy involving objects, involve the human, involve the collisions, the contacts, objects in the scene. And with that, we can define what kind of reflex we can play with. And the reflex, we also play around with different reflex agents. And I'm going a little bit detail on that. So here you can see different 3 categories, roughly, and the behavior that they have whenever they collide with sensorized objects, with a device for measuring the contact forces. Here you have stop collisions, you have active retraction reactions, and this could be Cartesian, joint retraction, a combination of them, and methods about back travelability with admittance, combinations, zero-G, super zero-G, and different combinations of those. And you can see that they're quite different. Here you can see them in slow-mo. Here you can see you have some features that are different. You have, here you can see, but the forces are different. Here you can clearly see that the velocities after the contact are different, and the distance, the distance that they take is also different. We also investigated secondary collisions. So whenever you collide with an object, what happens in the second stage, what kind of forces you transmitted. So we took all these features. We contact some experts in safety, in biomechanics safety. Some colleagues who have been working different topics in the area, including in vivo studies. And you evaluate different kind of hazards you can have. So evaluate, for instance, stabbing and what features are related to the damage that a stabbing could cause. So the maximum force in the point of contact, the distance that you take, the secondary collisions, the velocity that it's the robot, the reflex agents have in the secondary collisions. And with the studies we have, and with that information, we can map those to our taxonomy now. And we can look in the blue curve, in the blue part of the graph, we have what biomechanics would tell you. This is safe. These are the safety features that you are allowed to have. And in red, these are different controllers, different non-controller reflected agents, some are feed forward, that what are the results they have. And now you can look at them and very easily decide. It's a decision tree that you can say, oh, those are not good. I can use those for that specific scenario. And here's roughly what you got. This is a very simplified scene that we have some contacts. So just speed it up to make it easier. So here you have some contacts. You go on the taxonomy, evaluating, and here, naturally, stopping is a very safe criteria. And stopping is the standard one. It's the one that is certified. And it's the most common used one. And I'll just show like why it's not ideal. So you have a secondary collision now, which stopping would cause clamping. And this is the taxonomy. And now stopping is not a condition. It's not a valid condition. Super zero-G instead, it's a valid one. So the robot becomes super light and the person can move. This case, a stopping criteria is again okay to have because there is no chance of clamping. All the reflex engines would also be safe for this scenario. And finally, there is another one, But this time we cannot activate the super zero G that we had before. The robot cannot just go flying around because it has objects, it's carrying something that could be a hazard. So now we have an hybrid condition, could be an admittance controller, but this is a hybrid impedance controller. So this is the kind of behavior that you want to have to ensure safety, the human safety. But now, you can ask like if this is indeed safe, and I'm just gonna make an anecdote, so it's clear, I'm Brazilian, so I go to football. We have this, whenever I show this, I always tell like, in a long, long time ago when you have an amazing team, we had a manager that used to tell our best player in the 58s against Soviet Union, this is the plan. You go, you dribble the first, you dribble the second, you go around the corner, you score, you touch the pellet, you score. And the answer of the guy was, great for the manager, but have you already talked to the Russians? It's just like, yeah, it's just that, but someone needs to talk to the robot, right? Otherwise, we have like an amazing plan and this kind of behavior. Which, yeah, it's not ideal. So we need to embed those safety features in the robot. The robot needs to behave exactly as it is intended to. And these are the safety features that you embedded in the robot, the most critical ones, of course. You have the joint features that needs to be there. So the Cartesian space constraints that needs to be there as well. Manipulability constraints that need to be there. So all those are safety guarantee features that needs to be there such that the robot can actually be safe. Otherwise, you can have the perfect safety, physical safety guarantees, but if the robot doesn't behave safely, then what is the point? So we took those concepts and we moved to kind of a play scenario where we are looking at what could be extreme. What's one of the hardest challenges in robotics is carrying liquids, right? So how you can make those scenarios feasible? You need really to have precise manipulation. You need to really to have controllers that guarantees the conditions that we are planning to have. And this is basically emulating a spherical pendulum. So this comes from all the way 300 years ago, Moroccan T-trace devices. We just modeled the robotics like that. And we ensure that the robot has an amazing behavior to behave like that, so it doesn't drop any liquids. Because it's all model-based, and these features, the safety layers needs to be model-based because it needs to have like formal guarantees. We embedded, these always running 1 kilohertz, so we embedded MPC controller. It's basically a controller under constraints as well, and the time-bound constraints basically guarantees that the dynamics of the pendulum that we have are also matched by the dynamics, the constraints of the robot that you have. And all this running in loop, we give people to play around. So this is in Iros in Tokyo, and you give the cell phone to control the robot, and you're asking people just to break the robot. And this is a cool thing that the safety features need to have. You need to ask people to break things. Because this is where it cannot break. So in all those scenarios, and this is in Automatica, in two different scenarios, where you have like 40,000 people, and you're just giving the Xbox controller now for people to play and to break the system, and giving to kids to play or break the system, which is extremely scary. Kids are very good on breaking things. And it worked, that's the main thing. So that's what we wanted to have in a safety layer scenario. If you have that in the safety layer scenario, then you can build up. So here I'll talk very quickly about the understanding and reaction scenes. So this is basically me trying to break the robot as well. So this shows a little bit about the reactiveness that the robot needs to have. So I'm just trying to drop the ball, and the robot needs to react instantaneously to adapt for it. This is the scenario of teaching tasks, and again, teaching one demonstration with all the safety constraints that we had before embedded. And this is the same thing that they dropped the beer on me, but now without dropping, ideally. And extending to different scenes. So this is, I'll just go very quick on that topic because it's not the main idea, but the idea here is basically that once you have the basic constraints, the basic feature, the layer of the robot underneath, then teaching becomes easier and much more robust. This is an extension where you adapt also the reaction, the whole body adaptation of the robot in different demonstrations. But again, it's just the idea that if you have those safety features, then all this becomes much simpler to use and much more robust. And this is a whole body avoidance, while tracking, and executing the demonstrated task. I'm going to go in a little bit more details of this. I just want to highlight why this is important, understanding the robot embodiment as well, because we need to understand the human embodiment and tools that we can use for one, we can use for other. So this is a study that we are looking on the embodiment of the robot and particularly switching between the robot. So if you have used, for instance, RT, you know that sometimes the RT just takes completely different paths. And one of the main reasons because of that is because it has discontinuities in the new space. So we evaluated not a 6D robot in this space, position orientation, but an 8D scenario where we have the swivel angle and the switching between different parts, the discontinuous parts of the robot. We come out that different robots have different ones. I'll just jump here, what you see. So here are the KUKA discontinuities, which are continuously 8 spaces that the KUKA has, and the Franca Amica has 4. So if you know about them, then you know how to switch between different parts of the space. And if you guarantee that your RT is moving in a continuous space, the behavior will be continuous. I'll go in a little bit more details on that, but here the idea is that these maps, this information can be used not just to build new devices, new tendon-driven devices, but also to understand the human embodiment. All right, coming to human now, you have all these layers set, and now you wanted to have like a complex text together with the human. So here you're doing like a physical interaction. You are doing a cutting scenario where we have a cutting scene defined. Here you want to minimize the number of your graspings. So you're just playing around, you're discretizing the task, playing around like how you're gonna define this in a graph scene and define a grasp planner to execute it. And this is the scenario you got. You can just go quick on that, this is not the main part of it. But here is the idea is that the robot interacting with the human try to minimize the number of regraphs it needs to do to perform those 2 tasks. So one is grasping the area, cutting of a board, and the other is mounting a IKEA chair together. It's a bit boring movie because it's basically the robot moving the least as possible. But one thing that we got from these experiments is these conditions. Whenever I was cutting it, we were performing the task correctly, but basically my hand was always very, very bad, and the hands of all the subjects are all the same. Because we're looking at the task, we are not really looking on the safety, on the comfortable side of the human. So how humans feel about that. The task is being done, but not really nice for the person. So we embedded multimodalities for that, how we can get the features from the person and embed it to the robots. So naturally, like the most trivial ones, embedding natural language. Let me just embedded natural language. So how we embed a natural language, again, in all the safety features that I mentioned before. So basically here we can modify the trajectory of the robot, still maintaining the constraints of the task and the constraints that are previously defined for the robots. Different embodiment, of course, that's not that hard. And having this adaptation in real time, which is the critical part. This is just a model. I can go into details later. But you can also adapt that to stiffness and to force interaction. And then it comes to safety. If there is a clamping, you don't have the time to go in your computer and say, please stop doing that. But you wanted to have the robot to not have this kind of clamping scenario, but to tell the robot to, well, get lighter when you're close to me. And the robot will just change the stiffness with safety guarantees, with stability guarantees, with all the features that needs to be there in the lower level layers. Different parts of embodiment as well, so gestures, understanding. So if you're pushing something, your body tells a lot about the task that you're doing. So this is how you would do it. The embodiment of tells if you're doing an easy task or hard task, a forceful task or not. And this is very critical for human interaction in terms of understanding that, and in terms of mapping that information from one system to the other. So how you map that from the robot to the human to the robot. And this is just a very quick example as well. I'll go quick on that, but this is basically one demonstration that it's the same demonstration, but one is basically pushing task, what is swapping. So there are different tasks and the different embodiment because they require different forces. And this, if you're just doing a visual demonstration, you don't have information about the forces, but you do have the information about the embodiment of the person. And you can map that information and transfer that information to the robot. And in the end, what we get is scenarios. I'll just speed it up like here. So these are scenarios that you got that if you see in the lower joints, hopefully, yes, showing here. If you show in the lower joints, without demonstrating, just looking at the 3D task, the robot is able to adapt its posture in a way that it's easier to execute the task, because that was how it was demonstrated. So the embodiment, the transmission of forces and velocities are embedded in the demonstration and are given to the kinematics of the robot, who now can adapt to that. So this is very important, integrating those aspects, and of course integrating, as I said before, ergonomics and biomechanics. So how we embedded the biomechanics information. And here is a very simple example. So here's a very simple example. The same task that this is exactly the same task, but in one task the robot is posing, it's just a longitudinal cut in the board. And in one task, the robot is placing it in a way that requires the human to execute that task very uncomfortably, while in the second one is changing the orientation of the board, making it much easier for the human. So the robot knows the task, we know the task, it's just how the robot reasons about the task the human is going to execute. And when you do a human-human, that's kind of natural. You wanted, as I said, we wanted to find a consensus between you two. But the robot doesn't know your body, so it needs to understand the embodiment to be able to do that. So it needs to think about all possible ways you can execute the task, needs about all the possible kinematics you can execute at that point, and needs about all the possible muscle activity that you can get at that point, and then you can execute the task in a way that minimizes muscle activity while guaranteeing all the constraints that you have during the interaction. So we did that. We did some studies in terms of having the optimal planner that minimizes muscle activity, a random planner that the robot just decides, okay, this is the task I need to do, this is how I'm going to do it, and you figure, and humans will figure. And the last one in the red is basically we ask participants to manually pose the board where they would feel like comfortable interacting with, after playing with the robot, getting acclimated to the robot. And funny enough, this is the graph we got. So if you see, just to make it easier, this part, the bottom left is the most comfortable part, and the top right is the least comfort. Naturally, the random is everywhere, as the random planner would be. The optimal one kind of constrains the user to be around the comfortable space, and the user-defined one sometimes is good, sometimes not good. It's way worse than we expected. And even compared with the user-defined one, we could see reductions of 70% of muscle activity in the main muscles requiring executing those tasks. And it's basically because you're constraining the person to execute in an optimal way, muscle-related, muscle-oriented, of course. But as I mentioned before, this is quite time-consuming. It requires you to compute all possible kinematics, all possible muscle activity. That takes forever. So instead of doing that, we devised a pre-computing tool that computes all this information for you. So it computes the ergonomics and the muscle activity in different parts of the space. So you just need to, it's basically a lookup table at this point that you can just grab the information that you need. What is the optimal configuration for these kind of forces? And the robot will be able to do it and will be able to give you. This has been done. We're executing a new version of it now that should be available in a few months, is the Rapid Human Manipulability 2. So here we are integrating new spaces of the human, also evaluating the swivel angle, also integrating different kind of metrics of the human. So basically, different kind of joint limit configurations, biomechanically oriented joint limit configurations, dynamic manipulabilities, and so on. And the main thing here is that it's a very structured data. And because it's a very structured data, it's very prone for learning. And we wanted to make it available for the public exactly so they can look around and play with it and learn more about how we behave things so we can embed that in new configurations for human interaction. But just to wrap up, given the time, this is my view in terms of how we should bring the comfortable side into human-robot collaboration. This layered approach with formal guarantees all the way to the new features that we have and bring in a nice way. And just want to thank you all the students and all who did the hard work as well with me.
Few talks before where they were mainly focused on foundation models, right? I've seen one of your work was using large language models, but more for instruction, right? Do you see that some of those components can be used in some of the layers that you have been working on? And if yes, which one you think?
I think so. So I think foundation models are extremely powerful, but I think it's Ronald Brooks that says that we need to cut the tails. And cutting the tails means that we need to constrain that to places, especially when you have human interaction, places that we know where they work, and put them in safety boundaries. That means reducing the power that they have a little bit, yes, but that means that you have formal guarantees on them, and then you can deploy them safely. But different features you can embed, as I was showing in terms of kinematic tracking, interacting directly and having a dialogue on how to perform a task, or using that for task planning. If you build that on top of different layers that guarantee safety, then you know what's your worst case. And knowing what worst case kind of gives you the formal guarantees you need.
Okay, thank you, understood.